Okay. So today we're going to discuss experiments. And the things about experiments that you absolutely need to know are three things that every experiment deals with or accomplishes. One is that it accomplishes all four goals of science. Remember, they are to describe, explain, predict, and control. So an experiment can accomplish all four goals of science, whereas, for example, all the methods we've talked about so far were descriptive methods, and all they could do was describe. As a result of being able to accomplish that goal of explanation, experiments are also the only method that determines cause and effect. So they're the only method that accomplishes all four goals of science, and they are the only method that determines cause and effect. In an experiment, we also test the hypothesis. So the third thing that an experiment does is it allows us to test a hypothesis, which is a testable prediction. So you might ask yourself, if an experiment can do all that, why do we ever use any other kind of study? Why don't we always use an experiment? The reason is that experiments have certain requirements, and if we can't meet those requirements, then we're limited, and we must instead use a different method, okay? Also, some questions are not appropriate for experimentation. Like, for example, if you want to know people's opinion, you have to ask them, and that's what a survey is for. So, just as a general overview, just to let you know what an experiment is. In an experiment, we take a group of people, which is our sample, and we divide that sample into two groups at least. And those people in our sample have to be divided into the groups at random. So our subjects have to be placed into the two groups at random. The two groups are called the experimental and the control group. The experimental group is the one we're going to experiment on. We're going to do something to them or treat them a certain way. The control group is not going to get that treatment. They're only going to be there for comparison. So after we've done this to one group and not the other, we measure something about the people in both groups and see if one group is different than the other on this measure. And if it is, we assume it's because we did something to this group, the experimental group. And the thing that we do, that we experiment, what we do to people is called the independent variable, and what we measure about people is called the dependent variable. Okay? So we have here the three requirements of an experiment. To do an experiment, you have to have at least two groups that you're dividing people into, and of those two groups, one has to be just a comparison or control group. Okay? And you also have to have at least two variables, one independent, the one we control and manipulate on purpose, and one dependent, the one that we measure. And then also it requires that when we divide our sample into those two groups, that we do so through random assignment, meaning that everyone in the sample has an equal chance of getting put in one group or the other. And we'll explain later why that is. So, I got it, okay. So an experiment tests the hypothesis. It determines a cause and effect relationship. It also accomplishes all four goals of science. And we have so much control in an experiment. It is a very rigorous study. So we have so much control that we are going to have high confidence in our results. So those are the strengths of an experiment. But of course, we have a list of problems like we did for every other kind of study. And check out the size of this list, right? So we saw that when we went from naturalistic observation to laboratory observation, we gained some control, but we experienced an increase in the number of potential problems, right? So we had, in naturalistic observation, the main problem was observer bias. and then we got more control over that in a laboratory observation, and now we had observer bias and situational bias, right? Okay, so we're going to talk about these again, some of these that are just statements, and some of the ones that are bolded here are actual key terms. So we're going to come back to all this. Like I said, this is an overview. So first I want to kind of explain to you, how do we get to the point of doing an experiment? And often this starts with us making an observation. Now this observation can come from a formal study, like a case study or a survey or a naturalistic or lab observation. Or it can come from informally noticing something. And that observation may lead us to develop a hypothesis. So our example is that I'm a first grade teacher, and I notice that some of the children are reading at a much higher level than other children. And when parent-teacher conference day comes along, I find out that the kids who were getting hooked on phonics at home were the ones who were doing better. So their parents tell me, oh, they're reading well. I expected that because I bought this program for them called Hooked on Phonics, where they learn to read based on phonetics. And so this gives me an observation that those kids are doing better, which might lead to me making a hypothesis or testable prediction. That prediction being that Hooked on Phonics will increase the reading level of first graders. When I make a hypothesis, it applies to an entire population. So I mean that all first graders, for the most part, would benefit, let's say in America or something, would benefit from Hooked on Phonics. And I'm going to test that, okay? But when I go to test it, I have to conduct an experiment. That's how we test a hypothesis. And experiments are not tested on entire populations. They're tested on samples, right? And in fact, in an experiment, and this is important for you to know because it's on the test, in an experiment, the sample is usually not very good because we have so much control and manipulation that we're doing that we have to have a sample that's convenient to us, that we can get to, that we can look over, that we can control. So if I wanted to do a survey about kids' reading levels, I could ask teachers or parents all over the country by sending out some sort of survey or questionnaire or doing interviews or something like that, all of which are survey method research. But I could get a much larger and a more representative sample that way. But if I want to conduct an experiment, I have to beg a few classes or schools near me to allow me to use their first grade classrooms, right? So as a result, I'm going to have only people near me, right? I'm not going to have students from other parts of the country and so forth. So it's not going to be representative. I'm trying to do that less because I'm taping. So it's not going to be representative, and it's not going to be nearly as large. When we do correlations and surveys, we can use very, very large samples. When we do an experiment, our samples are typically limited. So if I ask you what are experimental samples like compared to surveys or correlations, the answer is usually that they're smaller and less representative. That's what usually is the case. Okay, so I've made this hypothesis about an entire population, and now I conduct an experiment, but I'm going to do that only on a sample. And I'm going to get data, the results of that experiment, right? The data that says this group of kids did better on Hooked on Phonics or did not. And that data is only about that sample, right? Those are the only people who took the Hooked on Phonics. So basically what happens is that I'm going to find that even though the data applies only to the sample, what I'm going to do with the data is I'm going to draw a conclusion. And what I do when drawing a conclusion is I come right back to the hypothesis and I say, does my data support my hypothesis or not? But of course, the data is only on a sample, and the conclusion and the hypothesis are about a population. So this is an example of what we call generalizability, right? This is an assumption we make in research that what's true of the sample is true of the population. So if Hooked on Phonics works for these group of kids that I do an experiment on, then it should work for most first graders in the United States. Now that may be true or it may be not true. And in order to make sure it is, we're going to keep doing the study over and over again and use different populations. You'll see that later. Questions at this point? Okay, so next we're going to talk about the steps in conducting an experiment. So there are 5 steps, and the first step is to state what is the hypothesis. So in the case of hypotheses, they're always formatted as A causes B. So A is the cause, B is the effect, A changes B in some way, and you can have a very general hypothesis like A changes B, or you can have a specific directional hypothesis, A increases B, or A decreases B. So for my study, I'm going to say that my hypothesis would be, does Hooked on Phonics lead to an increase in the reading level of first graders? And even though I just stated that as a question, I should not have, because hypotheses are not questions, they're statements. And we'll find out if we can support it. So Hooked on Phonics leads to an increase in reading level for first graders. So once I have a hypothesis, my next step is to determine what are the variables. The variables in a study, in an experiment, are seen in the hypothesis. Hypotheses are always stated as A causes B. And A is what we call our independent variable, and B is our dependent variable. So a variable is something that can change values, and we use 2 of these. One of these variables is something that we control and manipulate on purpose, right? So we're going to control and manipulate Hooked on Phonics. And then the second, the dependent variable, is what we are going to measure. Remember, the variables are never people. They're always either something you do to people, the independent variable, so we're going to give them Hooked on Phonics. And the dependent variable is something you measure about people. What we're going to measure is their reading level. So they're never people. So we went over a couple of examples to repeat those. Let's say that I'm doing a study on how alcohol affects your driving. Let's say that my hypothesis is that alcohol leads to impaired driving ability. Okay? So what is my independent variable? Alcohol is what I'm controlling and manipulating. And my dependent variable would be what? Driving, so how many mistakes they make on a course or something like that. Okay, so the third step is what we're going to do next. And the third step involves taking our sample and dividing it into at least 2 groups. Remember, we have to have at least 2 groups. And so we're going to divide it, but the important thing about step 3, is that we're going to divide people into these 2 groups through random assignment. Random assignment means that everyone in the sample has an equal chance of being put into one group or the other. And so, for example, everyone in this class, if you guys were the population, you would each flip a coin. And heads is one group and tails is the other, right? Okay, so we're going to do that at random, through random assignment. And it's going to lead to us having these two groups. So one group is called an experimental group, and one group is called a control group. So these are our two groups. By definition, we are going to give the independent variable, boy, that's crazy. We're going to give the independent variable to the experimental group, and by definition, we're not going to give the independent variable to the control group. But both groups will get the dependent variable because that's how we compare them. So in other words, an experimental group is the group that you do something to. The control group is the group that you just use as a comparison. So whatever you did to the experimental group, you don't do that to the control group. Okay? Now, the reason that we randomly assign people into these two groups, if I go back to the last slide, which is the last slide is slide 33. So random assignment means that that I am allowed to assume that the groups are equal. So we're going to talk later about something called selection bias, and it refers to choosing people in your groups in such a way that the groups are not equal on things that might be important to the results. And we are allowed to assume when we do an experiment that because we randomly assign people into these two groups, that the groups are equal. So things that might influence the results, reading level, could include how smart the kids are, right? Smarter kids are going to learn easier, so they'll learn to read faster. I'm assuming that for every smart kid in the experimental group, I have a smart kid in the control group. And for every not so smart kid in the experimental group, I have a not so smart kid in the control group. And anything else that could affect the results, all of that supposedly is equally divided. So we'll talk about that again. But that's what the random assignment is about. Okay, so the next step that we're going to do is the fourth step, excuse me. And the fourth step involves giving the variables to the groups. So in step 4, we actually give the groups the independent and dependent variables. So the simplest thing that I can do and still be called an experiment is to give the independent variable to the experimental group, do not give it to the control group, and go on for as long as I decide to do this study. Let's say I do it for 3 months or 2 months or something like that. So I give the experimental group the independent variable, hooked on phonics, and then I measure after 3 months the kids' reading levels. In the control group, I do not give them hooked on phonics, but at the end of 3 months, I test their reading level. And this study is not a good study because I'm missing some very important information, which is what? What am I missing? Let's say what it was like in the beginning. So let's say the experimental kids are now reading at the 3rd grade level. And the control group kids are only reading at the 1st grade level. I don't know if that's significant or not, important or not, because I don't know where they started. So the study that's on your slide 35 is much more likely to be a good experiment. In this case, this would be laughed out of science because we wouldn't even know what to make of that. So instead, what we're going to do is, step 4 is going to include first testing the dependent variable. In other words, what's the average reading level for the experimental group? What's the average reading level for the control group? Then, during these 3 months' time, we give hooked on phonics the independent variable to the experimental group and not the control group. Then we test them both again. Let's say they both started at the half grade level. So in other words, halfway through 1st grade. Not quite complete, right? And these kids went up from the half grade level to the 3rd grade level. These kids only went up from the half grade level to the 1st grade level. Now we see that there is, a difference between the groups that seems to be important. You with me?
Yes.
Okay. So, let me see if I want to tell you anything else. Oh, okay, I don't remember. So let's talk about the study I just mentioned on driving and alcohol. I want to ask you, if I were doing a study where I give some people alcohol and other people don't get alcohol, and then I put them on a driving course and see how many mistakes they make, like how many cones that they knock over or something like that, would it be important to study their to measure their driving ability before I gave them alcohol?
Yes.
Yeah.
Absolutely. So I would start in this case by the dependent variable testing their driving ability. Then I would give this group alcohol. The experimental group gets the independent variable, which is alcohol. The control group does not get it. Then after they've had alcohol and I've waited, let's say 15 minutes or 20 minutes for it to kick in, then I go ahead and give them the driving test again and see what kind of change did the alcohol make. Not just are they driving poorly, because they might have driven poorly before and I don't know it. Okay? So we often want to start by measuring the dependent variable first. The fifth step is dealing with alpha. Now, we are not allowed to look at this and just say, hey, look, these kids went up 2.5 grade levels and these kids only went up half grade level, so that means that since the experimental group did much better, that Hooked on Phonics works, okay? We're not allowed to eyeball it like that. We use a statistical formula called alpha to test the results of an experiment. There's only two things you need to know about alpha. The first thing you need to know is that alpha only is used for experiments. So correlations, anything else does not use alpha. Alpha is a formula that we only use with experiments, okay? And the second thing you need to know is what it means. So the last point on slide 36 tells you that alpha tells us what is the likelihood that the results we got in the study occurred by chance alone. Okay? So what we're going to do is we're going to use the formula, which you don't need to know and nobody's going to ask you to do anything with, okay? You're going to stick numbers into a computer and it's going to give you what is the alpha for this comparison. For example, if I compare where these kids in the experimental group started at the half grade level and where they ended up at the third grade level, it will give me an alpha variable for that, an alpha reading, okay? So let's talk about what that means. So alpha will always equal to some small decimal, like 0.10 or 0.06 or 0.05 or 0.01. And what that means is that if it comes out at 0.10, it means that 10 times out of 100 that I do this study and I use the same amount of people that I did in each group and I got this exact amount of change from the dependent variable before and after giving the independent variable. 10 out of 100 times that I do that, that change will be a coincidence. The only reason that they went up from the half grade level to the third grade level, 10 of the times that I do this out of 100, it will be a coincidence. The other 90 times out of 100 that I do this, it really was the independent variable that caused the dependent variable to change. In other words, it really was Hooked on Phonics that caused the reading level to change. Is that catching you? Okay. So 0.06 means that 6 times out of 100 that we compare these two numbers, the dependent variable before and after the independent variable is given. 6 out of 100 times, it's a coincidence. That change was not real. The other 94 times out of 100, the independent variable is what's causing the dependent variable to change. .05 means 5 times out of 100 it's a coincidence, and 95 times out of 100 it's really hooked on phonics that made that reading level go up. And .01 means 1 out of 100 times it's a coincidence, and 99 times out of 100 it is hooked on phonics, the independent variable that caused the dependent variable reading level to increase. Now, which is a larger number, .10 or .01? Which is larger?
.10.
.10 is a larger number, and the last example, .01, is the smallest number up here, right? So what we want, hopefully, is what? We hope that when we do our tests for alpha, that we get what? A smaller or a larger number?
Smaller.
Smaller. We hope to get the smallest number possible. We may not, we just hope that, okay? So science has cut alpha off right here, and we have decided that .05 is, and smaller is okay, and .06 and higher is not. Meaning that I'm willing to accept that 5 times that I do this in 100 times, the results are a coincidence, because 95 times sounds good to me. 95 times, it's not really 95% of the time. I'll say that, but that's not actually correct. But I'll say 95% of the time, that's going to be correct, okay? That in the independent variable really did cause the dependent variable to change. Okay, so if I get .06, that's 6 times out of 100, it could be a coincidence. And I'm not willing to accept that. So science had to cut it off somewhere, and that's where they decided to cut it off. Meaning that if my alpha, when I compare these two numbers, if my alpha test comes out at .06, I will not get published. So my results will not be seen by other scientists because it's insignificant. So whatever difference I saw was not enough that we can count on it to be likely to be true. We're just not willing to accept 6 out of 100 chances of error, but we are willing to accept 5 out of 100. Okay? So, and like I said, I'm simplifying how I put that. When you get into statistics, you'll realize that. But anyway, so that's the cutoff. Now, a couple of things that I'm going to ask you, and remember that the only 2 things you need to know about alpha are that it goes with an experiment, and it tells us what is the likelihood that the results we got are just a coincidence and not really the independent variable causing the dependent variable to change. So the first question is, will alpha ever equal 0? What's the answer? No, alpha will never equal 0. Equaling 0 would mean that there's no chance of error. But we make all kinds of assumptions when we do an experiment. Let me go over some of those assumptions right now, even though we'll repeat them again. One assumption is that I can work with a sample, and whatever's going to be true of the sample will be true of the population. In other words, that I have generalizability. So I assume that what's true of the sample is true of the population. Science understands that that's only an assumption. So there's things we're going to do about that. And one of them is we're going to have an alpha to tell us if that's never going to tell us 0. There's no chance of error, okay? Another assumption we make is that random assignment made these 2 groups equal on anything that might matter to the results, okay? We'll talk about this in a moment. And also, we assume that the only thing that's causing the dependent variable to change is the independent variable, okay? So in other words, we're assuming that the independent variable causes the dependent variable and nothing else. So because of those assumptions, alpha will never equal 0 because we realize that there's always a chance of error, okay? Or that this could be a fluke, in other words, that this would be an unlikely time. So the next thing we're going to do, and this begins our lecture for this class, is we're going to talk about potential problems in an experiment. But what I want to do, this is slide 37, and it has the key terms that go with problems, potential problems in an experiment. Okay? And what I want to do is I want to go back to slide 27, because 27 had a really longer list here, much longer list, not much longer, but longer, because it included things that aren't key terms. And I want to discuss some of these potential problems. So, one potential problem is that experiments are artificial. When we do an experiment, we control things and manipulate things to such an extent that it's not a typical natural environment, right? So for example, if I give hooked on phonics to kids to see if their reading level improves, I'm probably going to do it at school, in a desk, in a classroom, with a teacher watching, so a very academic setting where children have learned this means I'm going to learn, right? But when I buy Hooked on Phonics for my kid, and they're using it at home, they could very well be doing it at the kitchen table, right? While mom's making dinner and yelling at the other kid for poking at you while you're trying to learn, and the cat's chasing the dog all the way around the table. So it's a very distracting environment. Whereas I did the experiment in a very with no distractions, or very few distractions in comparison. So will it apply? I don't know, because this natural situation is not the same as an experiment, because it can be so artificial. There are ethical issues in an experiment. Now, psychologists have rules about ethics in how we treat people, and also how we go about doing research. And the ethics include things like we have to get people's informed consent. So they have to not only give their consent to participate in research, we can't just use them without them knowing, really. In most cases, naturalistic observation and such we do. But they have to give informed consent, meaning they know what could possibly happen or what the outcome could possibly be, anything that could be harmful to them. Okay? They also have to debrief. Psychologists have to debrief you if you're in a study. So if you did that participating in research quiz, you took a couple of surveys, in the last page, they didn't just usually say thank you without telling you something else about what the study was about, or if you want more information, write us at this address or something. Especially if you lie to subjects. You might lie to subjects. You might tell them, we're studying how much energy people have, or what they do here and there, and really what you're studying is body language. But if you told them I'm studying body language, that might change their body language. So basically what you're doing is you lie to them initially, and then you tell them the truth. You have to tell them the truth. And you have to provide any kind of assistance they might need as a result of finding the truth and being upset. Okay? So there are all kinds of ethical issues that guard how we treat humans and animals in research. Alright, not all questions are appropriate for an experiment. Some for ethical reasons, right? And others, which I'll come back to, well, I'll do that now. So I think we talked about if we wanted to know if being abused as a child, let's say physical abuse as a child, makes people more likely to have low self-esteem as adults, right? Well, we would never do that ethically, because to do an experiment on that would require us to take a group of kids, very young, randomly assign them to the controller of the experimental group. The experimental group we would abuse, that's the independent variable, and make sure everybody gets abused exactly the same way. And the control group we make sure doesn't get abused. And then in the end, we test their self-esteem, probably before and after, if we can test it if they're not that young. So that, of course, we would never do. We're not going to abuse people or hurt them in any way. So instead, when I want to know, is there a relationship between self-esteem and having been abused, I can't go and find experiments on that. Those do not exist. So what does that mean? Why is that important? Because if there's not an experiment, then I can't say for sure that abuse is causing the low self-esteem. Only an experiment tells us that one thing causes the other. Okay? So in other words, I'm going to have to rely on research like correlational research, which tells us two things are related, but it doesn't mean that one causes the other. They might, but we don't know from that kind of test. So what we would do is we would take a bunch of people and see who's been abused and who has low self-esteem, and see if those are the same people. Okay? And if you tend to have lower self-esteem when you have been abused. Okay? So basically, there's all kinds of questions that we wouldn't do for ethical reasons, and we would have to go to some other kind of study like a correlation, because an experiment requires that we manipulate and do something that we might not ethically be okay in doing. Also, some things are not appropriate for experiments, some questions, because, for example, if you want to know what people think about something, it's not about do this to one group and not do it to another. It's about asking them, right? So in that case, you got to use a survey, because if you want to know, you got to ask, right? You with me?
Yes.
All right, so we're going to go back now to the slide 37, which is missing the things that aren't bolded. The bold, once again, are key terms, okay? So we start with selection bias. And we've talked about selection bias before. This is where y'all are new, right? Yes? Because I've been going kind of fast. Okay, so we talked about selection bias in a survey. And now we're going to talk about selection bias in an experiment. So what I want to do is I want to not just tell you what it is in an experiment, but I want to make sure you understand the difference between selection bias in a survey versus in an experiment. Because even though it's called the same thing, it refers to something a little bit different. Okay? Make sure you're getting me over here. Okay, so I got selection bias. And what I'm going to do is I'm going to show you what selection bias is in a survey on this side, and here in an experiment. All right, so in a survey, we have a population of people, right? And we take from the population a sample that's going to be in our study. Selection bias here in a survey happens right here, right there, how I pick a sample from the population. So I make some sort of error in choosing a sample from the population. For example, I ask only people who read one magazine, or only people who go to this website, or something like that. So the solution, and by the way, the problem, let me say that first. The problem will be that the results of my survey will not represent the population, because this sample is not going to be representative. So the solution is to try to get a representative sample so that there is no selection bias. A representative sample is one that represents the population well. And what I do with this is, in order to get a representative sample, I try to get as large a sample as possible. And if I can get a random sample, which are actually very difficult to get, but if I can get a random sample, I go with that. You with me? Okay, so we've already talked about that. Now what we're going to talk about is an experiment. And what does selection bias mean here? Okay, well, experiments are interested in an entire population, and they're going to work on a sample, just like every other study. However, then we're going to break that sample into two groups, right? The experimental group and the control group. Maybe more, but at least one of each of those. And this is where selection bias can happen. So here, selection bias is the error that we make in choosing groups or selecting groups from the sample. So selection bias in a survey is about how we choose a sample. Selection bias in an experiment is how we choose groups from the sample. Okay? And of course, our solution is what? Do you know? What do we do to solve that? You know what we do right there. Huh?
And make it random.
Random assignment. Okay? The solution is to use random assignment. So it's really called random assignment of subjects into groups. So the sample goes into groups through random assignment. So this is how we solve that. That was step 3 in conducting an experiment. And I said if you don't have that, you don't have an experiment, right? So you absolutely have to have that. Now, there is something else you can do, and you don't need to know this, but I'm going to mention it. And besides random assignment, there's the concept of matching. So matching means that as I'm doing this study, I might decide that I'm going to assume that random assignment is handling problems for me. Like, for example, things that could affect the results. So I'm assuming things could affect the results without me being aware of it. But when the issue is selection bias, it means that the issue, the problem, is about the subjects themselves. So I'm going to erase this and put up our study again. All good? All right, you can get somebody else's. Y'all got to talk fast, man. Okay. So our experiment again is here's our sample, and we're going to divide it into 2 groups. We have an experimental group and a control group, and we randomly assign people to go from the sample to the groups. And we tested these kids for the reading level first, the dependent variable. The experimental group got hooked on phonics for 3 months, and then we tested them again. The control group did not get hooked on phonics. We just tested them again in 3 months to see how much they change without this particular reading program. Okay? So selection bias refers to what's different about these 2 groups, right? Like all the things that could possibly affect the results. I could have, if I have kids who are smarter in the experimental group than a control group, maybe they got better not because of hooked on phonics, but because they're smarter, and smarter kids learn more. They learn faster, let's say. It could be that I have more kids in the experimental group who like to read, or whose parents expose them to reading, all of these different things, right? Okay? So it could also be that the control group just happens to have more people who are going through a hard time, their family's going through a difficult time, the child is stressed at home. I gotta try to get this out. I'm sorry. About to die. Thank you. Before we leave today, we're going to take pictures of the problems that we're having in this classroom. Okay, so don't even go. Just stay right there. Okay, because I have to put your notes. Okay, so there could be all kinds of things that are, maybe more of these kids are getting to eat a healthy breakfast than in the control group and so forth. So when I randomly assign, I'm allowed to assume that for every kid here who's eating well, I have a kid here who's eating well. And for every kid here who's having trouble at home, it's making it hard for them to concentrate, I got another kid here like that, okay? And so forth. But I might decide, hey, you know what? I can't leave intelligence to chance. It's just too important. So in that case, I can do something called matching, which means that I take every kid in the sample and I test them, let's say, for IQ. And then what I do is I find everybody a pair. So if you two guys are about the same IQ, I pair you guys, okay? And then I toss a coin to see which one of you is going to be in the experimental and the control group. So I've made sure that I have a really smart person in each group, right? But I'm also flipping a coin because that coin flip takes care of everything else, supposedly. So according to the coin flip, how about things I didn't control for, like what's going on at home, or do your parents like to take you to the library? All those things, I'm assuming, are going to be equal because of the coin toss. Okay? So it's a huge assumption that we're making, but we are assuming that if we randomly assign, we do not have selection bias, and that meaning that the groups are equal on things that could affect the results. And once again, it's things about the subjects themselves. Okay? Now we go on to something called a confounding or extraneous variable. I do not believe this is found in your textbook. I'm sure you can Google magic it, but try to understand it here. Ask questions if you don't get it. So a confounding or extraneous variable, either one, whatever you want to call it, is something that you do during the study, you the experimenter, something that you do to treat the groups differently. You didn't mean to, but you did. And as a result, there is an error in your results. So it's a bias, right? A confounding or extraneous variable causes error. So let me give you an example. Let's say that I'm having these children in the experimental group. They are receiving Hooked on Phonics by staying 30 minutes after school to get Hooked on Phonics. Now, they also have to have the regular curriculum, right? Because it's the law that you have to have the reading curriculum for your state. So these kids over here in the control group, they're not getting Hooked on Phonics, but they're still getting the regular curriculum. So this tells me how much do kids change when they have the regular curriculum. This tells me how much do they change when they have the regular curriculum plus Hooked on Phonics. But remember, I'm assuming it's Hooked on Phonics that's causing this reading level to increase. Could it not be that just 30 extra minutes of any kind of reading curriculum might be improving their reading? Yes? Absolutely. So that's a confounding variable. I think Hooked on Phonics caused these kids to be reading at the 3rd grade level. Really, it was this confounding or extraneous variable. It comes in and it affects the dependent variable, but you don't know about it. You don't realize it's happening. So the way to control these is to think about your study and really try to conduct it in such a way that you minimize these confounding or extraneous variables. So for example, I could add another control group. And my second control group, I would give them 30 minutes after school, just let's say going to the library and reading for 30 minutes. And then I would test them again. So I would be able to say if these kids do better from Hooked on Phonics than if you just were reading a library book, right? Reading a library book is free, right? However, Hooked on Phonics costs money. So if I want to make sure that Hooked on Phonics is what's working, I have to make sure I separate it from anything else. The whole idea of an experiment is that we treat the groups exactly the same except for the independent variable. So if these kids are going to stay after school for 30 minutes to get Hooked on Phonics, and these kids are not staying after school, I'm not treating them the same. So I add another group that will stay after school for 30 minutes. So I'm treating these groups the same, but this group gets hooked on phonics, and this group does not. And therefore, that's the distinction. I still have to have a control group, because I still want to know what happens when you do nothing. Is hooked on phonics better than doing nothing? Is staying at the library reading an extra 30 minutes better than doing nothing? So I still need to know, how does reading level change over time for kids who are just getting the regular curriculum? Okay? You understand? So remember, this is not, you got to get it here. It's not in your book. A confounding or an extraneous variable is something that the researcher does during the experiment, and it affects the results of the study. In other words, it affects the dependent variable without the researcher understanding or knowing about it. The researcher doesn't know that what they're doing is causing a change in the dependent variable. Okay, and so the researcher might say, hooked on phonics works, when in fact it wasn't the hooked on phonics, it was just the 30 minutes after school. So we designed the study to control for those possibilities of confounding or extraneous variables. All right, so another problem that, yes?
Is it possible to have an experiment without a confounding variable?
Okay, a confounding variable is a potential problem, right? Is it possible to have the perfect experiment where you don't have any confounding variables? There might be one, but the thing about confounding variables is most of the time we don't know they're there, right? If we did, we'd control for them. So I don't know the answer to that. Maybe there's a perfect study, but we wouldn't know if it was or not. Now, we know good studies versus bad studies, okay? So when you pick studies to pay more attention to, researchers know to look for the ones that are, wow, they really controlled for a lot of variables, you see? But controlling for all those variables also makes them very artificial. So the artificiality becomes its own confounding variable, you know? Yeah. Any questions? Okay, so another potential problem in an experiment is lack of generalizability. Remember, generalizability means what's true of the sample is true of the population. And when we do one experiment, we don't know if the results for that one sample would apply to the population. So in order to make sure that what's true of the sample applies to the population, what we do is we replicate studies to make sure we have generalizability. We do the study over and over and on different samples and see if we come up with the same result. If we do, then that's how we know that there must be some truth to this, okay? Versus it being a fluke or a coincidence. So, I don't know if I told you about the prayer studies, did I? Okay, so a few years back,